Neptune looks calm, a distant blue world drifting quietly at the edge of our solar system. But beneath those clouds lies a mystery scientists still struggle to explain. A planet that behaves in ways that defy expectations. And the deeper we study Neptune, the stranger it becomes. Neptune orbits nearly 4.5 billion kilometers from the Sun, placing it at the far outer edge of our solar system. At that immense distance, sunlight is incredibly weak compared to what planets closer to the Sun receive. By simple logic, a world so far away should be extremely cold, quiet, and largely inactive. For many years, scientists assumed that Neptune would behave like a frozen sphere drifting silently through space, with very little internal activity. But observations quickly revealed something that did not fit that expectation. Despite receiving very little solar energy, Neptune releases more heat than it absorbs from the Sun. This means the planet is not just passively reflecting sunlight, it is actively generating energy from within. That discovery immediately raised questions because it suggested that something deep inside the planet is still producing heat billions of years after its formation. At first glance, Neptune's calm blue appearance can be misleading. The planet looks smooth and tranquil when viewed from afar, almost like a peaceful ocean floating in darkness. However, beneath those clouds lies a far more dynamic world. Neptune's atmosphere is actually one of the most active and violent environments in the entire solar system, with powerful winds and massive storms constantly reshaping the planet's surface appearance. Scientists believe part of Neptune's internal heat may come from leftover energy trapped during the planet's formation. When planets formed billions of years ago, gravitational forces compressed their interiors, generating enormous heat. In some planets, that heat slowly escaped over time. But Neptune appears to have retained more of that energy than expected, allowing the interior to remain active long after the solar system stabilized. Another possibility involves the structure of Neptune's interior. Unlike rocky planets such as Earth, Neptune is composed mostly of dense fluids and exotic forms of ice, water, ammonia, and methane under extreme pressure. These layers may slowly circulate deep inside the planet, transporting heat upward in ways that scientists are still trying to understand. This internal movement could help explain why Neptune continues to radiate energy. The planet's internal heat likely plays a role in driving its extreme weather systems. Neptune has the fastest winds ever recorded on any planet in the solar system, reaching speeds greater than 2,000 kilometers per hour. Such violent atmospheric motion would normally require a powerful energy source, and the heat rising from the planet's interior may be fueling this turbulent atmosphere. Interestingly, Neptune's neighbor Uranus does not behave the same way. Uranus, which formed under similar conditions, emits very little internal heat compared to Neptune. This difference has puzzled researchers for years. Two planets with similar sizes and compositions show completely different energy behavior, suggesting that something unique happened during their formation or evolution. One theory proposes that Neptune's interior mixes more efficiently, allowing heat from deep layers to escape gradually through the atmosphere. Uranus, by contrast, may have a layered structure that traps heat inside, preventing it from reaching the outer atmosphere. If this is true, it would explain why Neptune remains so energetically active while Uranus appears comparatively quiet. The mystery becomes even more fascinating when scientists consider that Neptune-like planets are extremely common throughout the galaxy. Many exoplanets discovered around other stars resemble Neptune in size and composition. If our Neptune behaves in such unexpected ways, it raises the possibility that countless other planets in the universe may also hide powerful internal engines beneath seemingly calm atmospheres. That is why the question remains so important. What exactly is powering Neptune? After decades of observation and modeling, scientists still do not have a complete answer. The quiet blue planet at the edge of the solar system continues to challenge our understanding of planetary physics. Beneath its tranquil appearance may lie processes that we are only beginning to understand. Neptune is home to the fastest winds ever recorded on any planet in the solar system. This distant blue giant, orbiting far beyond the warmth of the Sun, hosts storms and atmospheric currents that move at speeds exceeding 2,000 kilometers per hour. These winds are so powerful that they surpass the speed of sound on Earth, creating one of the most violent atmospheric environments known among the planets. What makes this even more surprising is that Neptune receives very little solar energy compared to planets closer to the Sun. At such a great distance from the Sun, Scientists originally expected Neptune to have a calm and relatively inactive atmosphere. Solar radiation drives much of the weather activity on Earth and other inner planets. Since Neptune receives only a small fraction of that energy, it seemed logical that its atmosphere would be cold, slow, and quiet. Instead, observations revealed the opposite: a planet with immense storms and incredibly fast-moving atmospheric currents. One of the most striking features of Neptune's atmosphere is the presence of massive storm systems. These storms can grow to sizes comparable to Earth itself, with swirling cloud patterns that move rapidly across the planet's upper atmosphere. The famous Great Dark Spot discovered by the Voyager 2 spacecraft in 1989 was one such example. A massive storm similar in appearance to Jupiter's Great Red Spot, but far more dynamic and short-lived. The existence of these extreme winds raises an obvious question. What is driving them? On Earth, wind patterns are largely powered by solar heating, which creates temperature differences that move air across the planet. But Neptune's weak sunlight cannot easily explain the incredible speeds observed in its atmosphere. This suggests that another energy source must be involved. Scientists believe that Neptune's internal heat may play a crucial role. Unlike many other planets, Neptune emits significantly more heat than it receives from the Sun. This internal energy likely rises from deep within the planet and interacts with the upper atmosphere, helping to drive large-scale atmospheric motion. In this way, Neptune's weather may be powered from the inside out rather than from external solar radiation. The planet's rapid rotation may also contribute to its extreme wind patterns. Neptune completes one rotation in about 16 hours, which creates powerful Coriolis forces in its atmosphere. These forces can organize winds into strong jet streams that circle the planet. Combined with internal heat and complex atmospheric chemistry, these rotating currents may amplify wind speeds far beyond what scientists initially expected. Another factor is the composition of Neptune's atmosphere itself. The planet is primarily made of hydrogen, helium, and methane. Methane absorbs red light and gives Neptune its deep blue color, but it also influences how heat moves through the atmosphere. Variations in temperature and density within these gases can create powerful pressure gradients, which may help accelerate winds to extraordinary speeds. Despite these theories, scientists still struggle to build models that fully explain Neptune's atmospheric behavior. Computer simulations often fail to reproduce winds as fast as those observed. This suggests that some processes inside Neptune are still not completely understood, especially the complex interaction between internal heat, atmospheric chemistry, and planetary rotation. Neptune's atmosphere also changes over time, with storms forming, moving, and disappearing in ways that remain difficult to predict. Unlike the long-lasting storms on Jupiter, Neptune's storms can appear suddenly and vanish years later. This constant change adds another layer of mystery to an already puzzling planetary system. For now, Neptune remains one of the most fascinating atmospheric laboratories in the solar system. A planet so far from the Sun should, by simple logic, be quiet and frozen. Instead, it hosts winds that outrun anything seen on Earth and storms that challenge our understanding of planetary weather. Until scientists can fully explain these forces, Neptune will continue to stand as a reminder that even the coldest worlds can hide incredible energy beneath their clouds. In 1989, NASA's Voyager 2 spacecraft made history by becoming the first and only probe to fly past Neptune. As it approached the distant blue planet, its cameras captured something astonishing in the atmosphere: a massive storm system later named the Great Dark Spot. This enormous swirling feature was roughly the size of Earth and appeared similar to Jupiter's famous Great Red Spot. Scientists initially believed they had discovered another long-lasting planetary storm that might persist for centuries. The discovery seemed to fit what researchers had already seen on Jupiter, where storms can remain stable for decades or even hundreds of years. The Great Red Spot on Jupiter, for example, has been observed since at least the 1600s. Because of that precedent, many scientists assumed Neptune's Great Dark Spot would behave in a similar way, slowly rotating through the planet's atmosphere as a permanent feature. But when astronomers looked again at Neptune years later using powerful space telescopes, something surprising happened. The Great Dark Spot had completely disappeared. The massive storm that once dominated Neptune's atmosphere was gone without a clear explanation. This unexpected disappearance forced scientists to reconsider their understanding of how Neptune's atmosphere behaves. Even more intriguing, New dark storms later appeared in different regions of the planet. These storms were not exact replacements for the original one, but entirely new systems forming in other parts of the atmosphere. Some lasted only a few years before fading away. Others changed shape, moved rapidly across the planet, or broke apart into smaller structures. This pattern revealed that Neptune's storms behave very differently from those on Jupiter. Instead of remaining stable for centuries, Neptune's storms are dynamic and temporary. They form, evolve, drift across the planet, and then disappear. The atmosphere seems to be in a constant state of transformation, almost like a living system that never stops changing. One reason for this instability may be the extreme winds that dominate Neptune's atmosphere. With speeds exceeding 2,000 kilometers per hour, these powerful currents can distort and tear apart storm systems over time. Unlike Jupiter's more stable atmospheric layers, Neptune's atmosphere may be more chaotic, preventing storms from surviving for very long. Another possibility involves temperature differences within the atmosphere. Neptune's internal heat rises from deep within the planet and interacts with colder upper layers, creating powerful convection currents. These rising and sinking flows of gas could trigger the formation of storms in some regions while weakening others, constantly reshaping the planet's weather patterns. Because of these processes, Neptune's atmosphere behaves more like a constantly shifting ocean of gas rather than a stable system of long-lived storms. Clouds form, move, and dissolve in response to forces that scientists are still trying to understand. Each new observation reveals changes that challenge existing models of planetary atmospheres. This unpredictability is what makes Neptune so fascinating to planetary scientists. Unlike planets where weather patterns remain relatively stable, Neptune seems to reinvent its atmosphere over time. Storms emerge suddenly, grow rapidly, and disappear just as mysteriously. In the end, Neptune's changing storms reveal a deeper truth about the planet. Beneath its calm blue appearance lies a world of constant motion and hidden energy. The storms that appear and vanish remind us that Neptune is not a quiet frozen giant. It is a dynamic planet whose atmosphere is continuously reshaping itself in ways that science is still trying to fully understand. Neptune's magnetic field is one of the strangest features discovered in the outer solar system. Most planets with magnetic fields have them roughly aligned with their axis of rotation, meaning the magnetic poles sit relatively close to the geographic poles. Earth, for example, follows this pattern fairly closely. But Neptune breaks this expectation in a dramatic way. Its magnetic field is tilted about 47 degrees relative to its rotation axis, and is also offset from the planet's center. This unusual alignment means that Neptune's magnetic field behaves very differently from the magnetic fields of planets like Earth or Jupiter. Instead of forming a neat, symmetrical structure, Neptune's magnetosphere appears lopsided and irregular. As the planet rotates, this tilted field wobbles through space, creating a complex magnetic environment that shifts dramatically over time. The discovery of this strange magnetic configuration came from measurements taken by NASA's Voyager 2 spacecraft during its flyby in 1989. Instruments aboard the probe detected magnetic patterns that did not match any previous planetary model. Scientists quickly realized that Neptune's magnetic field was not being generated in the same way as Earth's, where a molten iron core drives the magnetic dynamo. To explain this puzzle, researchers began examining Neptune's internal structure. Unlike rocky planets, Neptune is classified as an ice giant, composed largely of water, ammonia, and methane under extreme pressure and temperature. Deep inside the planet, these materials are believed to form dense, electrically conductive fluids rather than solid layers. These conductive fluids may circulate within the planet's interior, moving slowly but powerfully under immense pressure. When electrically conductive materials move through a rotating environment, they can generate magnetic fields through a process known as the dynamo effect. On Neptune, this dynamo may not occur in a central core, but instead in a shell-like region located closer to the outer layers of the planet. Because the dynamo region may exist in a relatively thin shell rather than deep at the center, the resulting magnetic field becomes distorted and uneven. This could explain why Neptune's magnetic field is both tilted and offset. Instead of forming a stable, centered dipole field like Earth's, it produces a magnetic system that appears chaotic and asymmetrical. The consequences of this unusual magnetic field extend far beyond the planet itself. Neptune's magnetosphere interacts with the solar wind. the constant stream of charged particles coming from the sun. Because the field is tilted and offset, these interactions change dramatically as the planet rotates, creating fluctuating regions of magnetic activity around the planet. Scientists also suspect that Neptune's unusual magnetic structure may influence its atmosphere and auroras. On Earth, auroras appear near the poles where magnetic field lines funnel charged particles into the atmosphere. On Neptune, however, the tilted magnetic field means auroras may appear at unexpected locations across the planet, rather than being confined to polar regions. Despite decades of research, many aspects of Neptune's magnetic field remain mysterious. The exact depth of the dynamo region, the composition of the conductive fluids, and the internal dynamics driving these currents are still not fully understood. Without another spacecraft mission to Neptune, scientists must rely largely on computer models and distant telescope observations. For now, Neptune's magnetic field remains one of the most intriguing puzzles in planetary science. It reminds researchers that the interiors of giant planets are far more complex than once imagined. Beneath Neptune's calm blue clouds lies a hidden system of moving fluids and electrical currents, generating a magnetic field unlike anything else in the solar system. If you enjoy exploring the most mysterious worlds in our solar system, subscribe now. Because the deeper we explore space, the more mysteries we discover. Deep inside Neptune, pressure reaches levels that are almost impossible to imagine. Thousands of kilometers beneath the visible clouds, the weight of the planet's atmosphere compresses matter with tremendous force. Temperatures rise to thousands of degrees, and pressures become millions of times stronger than what we experience on Earth's surface. Under such extreme conditions, the chemistry of familiar molecules begins to behave in completely unexpected ways. One of the most fascinating processes scientists believe may occur inside Neptune involves methane, a gas that is abundant in the planet's atmosphere. Methane molecules are made of carbon and hydrogen atoms. Under normal conditions, these molecules remain stable. But deep within Neptune's interior, the crushing pressure may force these molecules to break apart, separating the carbon atoms from the hydrogen. When carbon atoms are subjected to immense pressure and heat, they can rearrange themselves into crystal structures. On Earth, this process produces diamonds deep beneath the planet's crust. Inside Neptune, scientists suspect something similar could occur, but on a much larger and more dramatic scale. The carbon released from methane could crystallize into solid diamonds. Once formed, these diamonds would be heavier than the surrounding fluid layers of the planet. As a result, they would slowly sink deeper into Neptune's interior, falling through dense layers of superheated material. This process has been described by scientists as a type of diamond rain, where solid carbon crystals descend toward the planet's core. Unlike rain on Earth, however, this process would occur in total darkness and under extreme conditions. These diamonds could form in large quantities, gradually drifting downward through thick layers of fluid composed of water, ammonia, and methane in exotic high-pressure forms. The journey of these crystals toward the core could take long periods of time as they slowly move through the planet's dense interior. Laboratory experiments on Earth have provided some evidence supporting this idea. By recreating extreme pressures and temperatures similar to those inside Neptune using powerful lasers and shock compression techniques, researchers have observed carbon atoms forming diamond-like structures from methane-rich materials. These experiments suggest that the conditions required for diamond formation could indeed exist within ice giant planets. If diamond rain truly occurs inside Neptune, it could also play a role in the planet's internal energy. As diamonds form and sink, gravitational energy may be released, converting potential energy into heat. This process might contribute to the extra heat Neptune emits into space, helping explain why the planet radiates more energy than it receives from the sun. This idea also helps scientists understand why Neptune and Uranus behave differently. Although both planets are classified as ice giants, Neptune emits significantly more internal heat than Uranus. Differences in internal processes, such as diamond formation and sinking, may help explain why Neptune appears more active and energetic. Still, many questions remain unanswered. Scientists cannot directly observe Neptune's interior. So much of what we know comes from models, simulations, and laboratory experiments. While the theory of diamond rain is strongly supported by physics and experiments, the exact details of how often it occurs and how large these diamonds might be are still uncertain. If the theory is correct, Neptune may contain one of the most extraordinary environments in the solar system. Far beneath its calm blue clouds, carbon crystals could be forming and falling through the planet's interior like glittering snow in darkness. In that hidden world, the same substance used for jewelry on Earth may be part of a slow, cosmic storm taking place deep inside a distant planet. Neptune has a neighboring planet that seems, at first glance, almost like its twin, Uranus. Both planets belong to a category known as ice giants, a class of planets composed largely of water, ammonia, and methane under extreme pressure. They are similar in size, mass, and overall composition. Because of these similarities, scientists long assumed that Neptune and Uranus would behave in nearly identical ways. Yet when astronomers began studying them more closely, they discovered something puzzling. Despite their similarities, the two planets show dramatically different energy behavior. Uranus emits very little internal heat into space. In fact, it radiates almost the same amount of energy that it receives from the sun. Neptune, on the other hand, releases far more heat than it absorbs. Measurements show that Neptune emits more than twice the energy it receives from sunlight, suggesting that powerful processes are occurring deep inside the planet. This difference has profound consequences for the atmospheres of both planets. Neptune's excess internal heat appears to drive its violent weather systems and powerful winds, which can exceed 2,000 kilometers per hour. Uranus, by contrast, has a much calmer atmosphere. Although it still has storms and cloud activity, the overall energy driving those systems is far weaker than what is observed on Neptune. One possible explanation involves the internal structure of the two planets. Scientists believe that Neptune's interior may allow heat from its deeper layers to move upward more efficiently. If warm material can circulate through the planet's interior, that heat can eventually escape into the atmosphere and space. Uranus may have a more layered internal structure that traps heat inside, preventing it from escaping easily. Another theory suggests that the difference between the planets may be the result of ancient cosmic collisions. Uranus is famously tilted on its side, with an axial tilt of about 98 degrees. This unusual orientation may have been caused by a massive impact early in the solar system's history. Such a collision could have disrupted the planet's internal layers, possibly trapping heat deep inside and preventing it from reaching the atmosphere. Neptune, by comparison, may have avoided such a catastrophic event. Without a massive collision altering its structure, the planet's interior may have remained more stable, allowing heat to escape more freely over billions of years. If this idea is correct, Neptune's energetic atmosphere could be a direct result of a quieter formation history. However, the collision theory does not fully explain all the differences scientists observe. Computer models of planetary formation still struggle to recreate the exact conditions that would produce such a dramatic contrast between two otherwise similar planets. This suggests that other factors, perhaps involving chemical composition or internal layering, may also play a role. Another possibility is that Neptune's interior experiences stronger convection. Convection occurs when warmer material rises and cooler material sinks, creating a slow but powerful circulation of matter. If Neptune's interior mixes more actively than Uranus's, that movement could transport heat upward, fueling the planet's atmospheric activity. Understanding this mystery matters far beyond our own solar system. Many of the exoplanets discovered around other stars are similar in size to Neptune and Uranus. If two nearly identical planets in our solar system can behave so differently, it suggests that ice giants across the galaxy may also show a wide range of internal structures and atmospheric behaviors. For now, the Uranus-Neptune comparison remains one of the most intriguing puzzles in planetary science. Two planets formed in the same region of space from similar materials during the same era of planetary formation, yet they evolved into worlds with very different internal energy systems. Until scientists can study them more closely, the reason for this divergence will remain one of the great unanswered questions about the outer planets. Neptune may seem like a distant and isolated world at the edge of our solar system, but its importance reaches far beyond our cosmic neighborhood. In recent decades, astronomers have discovered thousands of planets orbiting other stars, known as exoplanets. Among these discoveries, one category appears again and again: planets similar in size and composition to Neptune. These so-called Neptune-like, or sub-Neptune planets are now believed to be among the most common types of planets in the galaxy. This discovery changed how scientists think about planetary systems. For many years, astronomers assumed that planets similar to Earth or Jupiter might dominate other star systems. Instead, observations from space telescopes such as Kepler revealed that intermediate-sized planets, larger than Earth but smaller than gas giants, are extremely abundant. Many of these worlds share characteristics with Neptune, including thick atmospheres rich in hydrogen, helium, and methane. Because Neptune is the closest example of this type of planet that scientists can study in detail, it has become a crucial laboratory for planetary science. By observing its atmosphere, magnetic field, internal heat, and weather systems, researchers gain valuable clues about how similar planets might behave around other stars. Every mystery uncovered on Neptune helps scientists refine models used to interpret distant exoplanets. One of the biggest lessons Neptune offers is that appearances can be deceptive. From afar, the planet looks calm and simple, a smooth blue sphere drifting quietly through space. Yet beneath those clouds lies an incredibly dynamic environment filled with violent storms, supersonic winds, and complex internal processes. If such activity exists on Neptune, similar processes could be occurring on countless Neptune-like planets across the galaxy. Another important insight comes from Neptune's internal heat. The planet releases far more energy than it receives from the Sun, a phenomenon that still puzzles scientists. If this kind of internal energy generation is common among ice giants, it could influence the atmospheres and climates of many exoplanets. Some distant worlds that appear cold from their distance to their stars might still be internally active. Neptune's unusual magnetic field also offers valuable clues. Its tilted and offset magnetic structure suggests that planetary dynamos, the processes that generate magnetic fields, can work in very different ways from what scientists observe on Earth. Understanding how Neptune produces its magnetic field may help researchers interpret magnetic activity detected on exoplanets light years away. The planet's atmosphere adds yet another piece to the puzzle. Neptune's rapidly changing storms and powerful winds reveal that planetary weather systems can behave unpredictably, especially when internal heat interacts with thick atmospheres. If similar dynamics occur on exoplanets, their climates may be far more complex than early models predicted. Studying Neptune also reminds scientists that planetary evolution can take many paths. Neptune and Uranus formed in similar regions of the solar system, yet their internal heat and atmospheric behavior differ greatly. This suggests that even planets with similar sizes and compositions can evolve into very different worlds depending on their histories. Future missions to the outer solar system could dramatically expand what we know about Neptune and ice giants in general. New spacecraft equipped with advanced instruments could measure atmospheric chemistry, internal structure, and magnetic fields in much greater detail than Voyager 2 was able to do during its brief flyby in 1989. These data would help refine our understanding of how these planets work. Neptune may teach us something profound about the universe, that the most common planets in the galaxy may be far more complex than we once imagined. By unlocking the secrets of this distant blue world, scientists are not just learning about a single planet, they are gaining insight into countless unseen worlds scattered throughout the Milky Way. Neptune remains one of the most mysterious planets we know, a distant world of violent winds, strange magnetism, and hidden energy. A planet that continues to challenge scientific understanding. And until we return with new missions, its secrets will remain hidden beneath those deep blue clouds. Subscribe for more cosmic mysteries and deep space discoveries. Because the universe is full of worlds we are only beginning to understand.